My name is Manish Naik. I work as a technology principal in BP in a team that's called Digital Innovation. Our team deliberately looks at technology first innovation. So we look at the horizon of emerging digital technologies and pick specific areas that no one in BP is looking at. And based on our understanding and experience of the oil and gas industry, we think those technologies are going to make a difference. So we start from there deliberately. And today, I'm going to talk to you about an example which we have worked with Bonsai. Varsha is here from Bonsai. And Wood, Prabhu is here from Wood. They would join us later on the panel. And the specific use case is in the area of well completions. This, this area sits in historically what was known as upstream. Now we call it production and operations. And the specific area where we have deployed this is in Gulf of Mexico. So I'm not a completions engineer, but I ran this past our subject matter expert, who is a completions engineer, who is effectively one of the 6 people in BP who does this for a living. And in his own words, eventually this use case will allow him to work on some other cooler areas in low carbon, such as carbon capture storage and geothermal, where his skills could be applied. So this is effectively looking at potentially automating the entire process end to end. But we start with, let's first start with understanding what well completions is and what part of well completions this use case sits in. So once you have drilled a well, before the production begins, you have to complete it. And the process of completing it is known as frac packing, which effectively, there's a substance, let's call it mud, which you have to drop through the annulus, and effectively you create a pack at the base of the well. And the quality of the pack is really important for various reasons, because you want to pack it well, you want to pack it quickly, and you want to pack it effectively such that the hydrocarbon that is producing out of it is coming out at an optimum rate, and there's no wastage from a safety standpoint, environment standpoint as well. And this is where the sort of the well completions engineers have, this is a big industry, and they have been, these guys are skilled, and the specific individual, Karthik, has been doing this for 30 years, and he uses his intuition in a frac packing job, which is effectively could be between 12 hours to 72 hours of really stressful work, where the individual is looking at a simulator and is trying to change the input parameters. The input parameters are pressure, temperature, solvency, and various other variables to look at effectively a pressure curve. And the pressure curve is what they then base their judgment on to understand whether the frac pack is complete and optimum or not. So our task at hand here was to see whether or not we could do this using AI and a specific kind of AI, and I'll come on to that in the next slide, and eventually see whether or not, so first test whether or not the AI could perform the same task at the human level, and then see whether or not, from our benchmarks in the past, whether the AI can beat the human performance as well in terms of optimization. There's loads of value if you can improve on the optimization side. I think I've been listening to this various talks at this conference, and I think most of the folks here understand the value of increasing sort of 0.1% of an optimization result as well. So there's tons of value both on the rig time in terms of the amount of time we would save during operations, as well as dollar value on increased production. So the size of the prize is big if we can crack this. And that's sort of the overall goal. And I'll talk a little bit about how we went about doing this, but I'll first start with the technology. So I think most of you would have heard buzzwords like AI and machine learning, and specifically machine learning at a high level. All kinds of algorithms sits in 3 different areas, and I'll give examples to explain this. The first area is supervised learning. This is effectively, you train the machine by feeding it data, and over a period of time, the machine learns. So feed the machine pictures of cats, 100,000 pictures of cats, and gets to recognize cats and differentiate it with foxes, etc. That's supervised learning. And that same concept applies to various different types of data, textual data, tabular data, time series data, but it's the same thing. You feed the data, machine learns, and that's supervised learning. Examples like equipment health monitoring. I've seen few talks about things like equipment health monitoring. That's basically supervised machine learning. 95% of the work that you hear in machine learning is in supervised learning. Unsupervised learning is where you don't label the data when you feed it to the machine. So you just basically throw data at machine and the machine identifies patterns. Continuing with the image analogy, let's say you want to feed the machine with pictures of fruit basket with different fruits in it, and you feed like 10,000 images of those, and over a period of time, the AI would start clustering different fruits, saying, okay, these type of fruits are here, these types look similar, these types look similar, and then you can say, then you can label it. That's an apple, that's a banana. So that sort of clustering is a big use case of unsupervised learning. And very little happens in that space as well. It's still in research in terms of what you can actually deliver. And the third area is reinforcement learning, which is what we used for this use case. Now, I've often struggled explaining reinforcement learning to people who probably haven't heard about it before. So I think it's best to explain with an example. Imagine you want to design a robot that has to move from point A to point B by avoiding obstacles in the room. That's your task. Where you would start with is you would effectively create a simulator of the same environment, like a video game of the room, and represent all the obstacles in the room as well. And then the software agent, you let the agent go, and the agent takes one step, looks around, not hit an obstacle, I'm good. Another step, not hit an obstacle, I'm good. Another step, obstacle, start again. So it goes from being absolutely rubbish at start of doing what it's doing to eventually over iterations inside the simulated environment, becoming superhuman and going from A to B. Never fails. And it compares the state against this notion of a reward. And that's effectively where I'll come on to when we talk about solution design. So that's the notion of learning in simulation iteratively and starting from scratch and eventually sort of learning, course correcting on the basis of a reward. So that's reinforcement learning, and that's the technology we chose for this project. In terms of selecting who to work with, so this is an area which at the time when we started doing this, this was getting a lot of press, and you would have seen videos of the Atari game where the machine finds a way to like immediately in one go beat the computer, or even things like AlphaGo, where the software agent has beat the world's #1 Go player 4-1. It was a big deal in Asia. It was like all over the news. And so those things were all reinforcement learning related. Gaming is where it had its biggest success. And if you wanted to do something with this technology in the industry, you had to effectively work with open source code. You had to find talented people. You had to go to probably universities where there's research happening in this area. And why would they want to work with us when there's so many other cool applications? So that's where I think we spotted a company called Bonsai, which later got acquired by Microsoft. And Bonsai was in the business of, and Varsha can tell this to you better than me, but Bonsai was, I think still is, in the business of bringing the success of reinforcement learning from gaming into industry. And specifically, these kinds of industries that we are representing here is where there is a sweet spot for a few reasons, and I'll come on to that in a minute. So, I described the iterative nature of the process before, and effectively what we had to do was we had to represent that logic in the frac packing process. One of the big reasons why this project was successful was because if you think about how the completions engineer works today, their work effectively is looking at a simulator. The simulator exists. The entire frac packing process is structured. The input parameters and the output variables are structured inside the simulator, and then the engineer takes a decision based on that. So that environment exists, And that's a key requirement for reinforcement learning, especially if you're doing model-free type of reinforcement learning. So that was there. The ways of working did not change for the engineer, and that was like the one of the biggest reasons why this worked. The other area where we had to this took about 2 to 3 months, but basically what we had to define was we had to continue to recalibrate the reward mechanism. How do you define how to penalize the agent or not? So after every time step of the pressure curve, we had to come up with a root mean square error was effectively what we chose on, and that factor effect was something that we had to choose to understand that if it goes beyond these parameters, then you penalize the agent and tell that it's doing something wrong. And if it's within that particular parameter, then you give a thumbs up. And then it keeps learning in that iterative loop, in this loop over a period of time, and eventually goes from not knowing what to do, just like the robot example that I gave, to matching human performance. And in the words of the frat packing engineer, Karthik, he says that he enjoys even looking at. So now the agent has become so good that it even predicts where the curve is going to be at 5 minutes earlier. And he says he enjoys looking, and he's like shows the junior engineers, see, it's going to go there, and it actually ends up going there. So they are building confidence in the system and trust in the system. And that's why eventually he thinks, this is not going to be anytime soon, but I think eventually, probably in a 5-year time frame, he would just be able to step back and observe what the agent is doing and not interfere. So the typical project phases for an activity in reinforcement learning is you start with the brain design. So the terminology that Bonsai uses for the agent is a brain. So you start with the design factors that I described, where you design the reward mechanism, you design the environment that you're going to train the agent in, and then you start the training. So training is effectively compute intensive, and depending on the environment and the complexity of the environment, this could take anything from days to weeks. In our case, it was a few weeks, and you do this over an iterative period. You go back to the brain design, you tweak the reward mechanism, and you keep doing this in a loop. And finally, there's the in this process, you prove success first inside a simulator. You can imagine this is a safety critical environment. So you prove success in a simulator, and only when you are very confident of the results, then you deploy it in a real world environment. And even that deployment has the human in the loop. So if the decision is still rests with the completions engineer in that context. So I want to focus a little bit on the lessons learned, but where we are going with this is currently live in Gulf of Mexico, but we see applications in other regions, as well as applications beyond traditional well completions into things like carbon capture storage and geothermal, where similar skills are applied. So I think I touched a little bit on the results. In terms of our vision for this specific use case, we want to take it from its current state, where it is suggesting the results to the completions engineer, and the completions engineer is then either overriding it or going with its results. We're going to keep tracking it, retrain the brain every 3 months, develop trust in the system with the completions engineers, and eventually get to a point where it's going to be like a real-time decision-making scenario, where the way we will develop this is the simulator effectively will be able to take decisions directly regarding well completions, and there will be a way for the completions engineer to intervene if they wish to do so. And you can imagine the next step after that is to take the human out of the loop, which we may not necessarily want to do, depending on how the results progress. But at least we do know that there is a lot of demand for these skills in other lower carbon areas, where these skills could be transitioned, where effectively the same skills could be deployed from a human standpoint first, and then eventually technology could take over. So what were some of the lessons learned here? From a technology standpoint, this technology, the biggest challenge, so if you were to talk to someone who's a critic of reinforcement learning, the first thing they would say is, it doesn't work. And the reason why it doesn't work is because it works great inside a simulator, and there's a reason why there's success in gaming, but when it comes to real world, it just doesn't work, because the difference between what is in a simulator and real world is just never going to be the same, right? So in this use case, it's called the sim to real gap, that didn't exist, because even today they use the simulator while making that decision. So that didn't exist, and there are some other use cases where that gap is really small. So the sim to real gap is something that you should evaluate before going into any project with model-free RL. I think from a people standpoint, we hit gold on this project because the subject matter expert completely embraced it. You can imagine going into this conversation with someone where you say that this technology might eventually uh, make some of the things that you do redundant, and you'd be sort of focusing on other more interesting areas, and people would have different reactions to this. But in this instance, the SME championed it and is going across the company telling people that this is the way of the future, we should embrace it, and we should deploy our skills somewhere else. So that was key, otherwise this project would have never taken off. And the data scientist in this instance, Andrea, she comes from a reservoir optimization and a drilling background. So if you are looking for a data scientist, you're looking for perfect data scientist, you're looking for three skills. You're looking for someone who has computer science skills, statistics skills, and the subject matter expertise. This person didn't have the stats, but had two. That's pretty good, and I think that was a big reason why we succeeded in this case as well. So this is where I think Prabhu would be able to talk about as well. But we had a mix of our squad was a mix of internal and external resources. So we had BP staff who were the SMEs and the data scientists. We had the AI engineers from Bonsai who brought in the reinforcement learning skills and the tooling knowledge associated with it. And then we had Wood who represented both the development, the architecture, and the scaling side of things, as well as all the breadth of the subject matter expertise in this area that Wood have. So we really had got together a squad of three different companies, but worked as one team in one squad, and then that was effectively the team that worked in an agile fashion to take it forward. So that balance was key. We wouldn't have been able to do this by ourselves. And lastly, I think the success the proof is in the pudding. So this is not done yet. We want to reap more benefits out of it, and the continuous training of the agent is crucial. And we are doing this for the first time as well from in the reinforcement learning perspective. So currently we have said every 3 months we will look at the data that has been generated, and we will retrain the brain. We are currently on our 53rd iteration of the brain, which is pretty good going, and we are still very confident of the results that are being produced. It is going in the positive direction that we want it to. So from that context, it has been successful. I would say though, this is the second project that we tried with reinforcement learning. The first one was considered, although successful, a little bit risky, so it's still on the project backlog. So as things are in innovation, not everything works, but this one did, and we've learned lessons from it. And I'm very happy to take questions in the panel on this use case and others. Thank you.